Okay, I think the recording has started, uh, and it's already 6:12. Sorry for the delay. So I hope my audio and screen is visible. If so, we can just start. So, okay, thank you for coming. Welcome to week 6 live discussion session for the NPTEL course on reinforcement learning. So in the previous weeks, what we have looked at was the different uh, methods in which we can basically evaluate a particular policy, right? So we had looked specifically at the value iteration method and the policy iteration method. And also we had proved like uh, rigorously that the policy iteration method and the value iteration method both will converge to the same optimal policy and the same optimal value function, just that the policy iteration converges in far fewer iterations as compared to the value iteration steps. Okay, so that was what we had looked at. So today the idea is to give an introduction. I mean, I don't need to introduce it explicitly. We have been so far doing that only, but just to write it down. So we'll look at something known as dynamic programming. Okay. So till week 5, whatever we had done so far comes under the domain of dynamic programming. Okay. I'll just highlight it. Okay. So before I start, any idea what do we mean by dynamic programming? If you're from a CS background, then maybe you can answer it. But just to give a quick one-line summary of what exactly we mean by dynamic programming. You know? Okay, so the idea behind dynamic programming is as follows. You basically what you do is you compute solution for an n-step subproblem and use it to solve for the n plus 1th step subproblem. So it's sort of an iterative process. What you're doing here is that whenever you have a solution for an n-step problem, you use that iteratively to update and predict, or rather solve for the n plus 1th step solution, and then for the n plus 2th solution, and so on. So this is an iterative fashion mode in which dynamic programming works. Okay, so just to give you a very pictorial representation of how the backup works. So this is a diagram that I've directly picked up from the Sutton and Barto second edition. So I'm just drawing it here. So let's say you have some initial state S. Okay, so from the state you can take multiple different actions, right? So here, in this case, the white bubble corresponds to state, and the black dots, the smaller black dots, corresponds to action. Okay. Okay, I think it hasn't updated yet. Maybe just let me see. Okay, let me try and rejoin. Just a second. I'll just try to rejoin. I think some issue came up with the screen sharing. You can hear me properly, right? Is there some internet issue from my end? At least from my laptop, no, right? Okay, audio is clear. Shows I can't join with the same Wi-Fi with here. Okay. Yeah, okay. I know. Okay. So I was saying the white bubble here corresponds to a state and the black dot here represents some action. Okay. So from an initial state S, I take certain actions, and after for a given state S, if I take action A, whatever I get, the evaluation is some immediate reward R. Okay. And then I go to some next state S1, and then correspondingly I take another action. So there are a bunch of different trajectories that you can see over here, right? And this goes on till the episode ends, right? So you see, this is one way to look at it. So now if you look at this quantity over here, this blue rectangle that I have drawn. So this bunch of black dots tell me that this is nothing but my policy A given S. It's basically the probability that I select action A when I'm in state S. Okay, you can see this clearly. And what this green box corresponds here in the second step is basically the probability of me going to state S prime given state S and action A. Okay, so these are the two different probabilities that this shows, right? And you call this as the mm, full backup for vpi. What is vpi here? Vpi is basically the value function associated with state S. Okay. And similarly, if I were to draw it for the qpi, okay. So what you say is, I don't start with an initial state S. Instead, I start with a state action pair because that's what my Q function tells me. It tells me that at state S, you first take action A and thereafter follow policy pi. Okay. So we start with a state action pair, and based on this on that, you get different states, and from there you get bunch of different new actions, and this goes on till you reach some terminal state, or the time horizon of the episode ends. Okay, so this you call it as the full backup. This you call it as the full backup for q pi s comma I. This is p pi of s. Okay, so far so good. So this is what the basics of dynamic programming was, right? And if I were to write it down, so this is how it looks kind of. So you have v of n plus 1 s is equal to max of a expectation r s comma a plus gamma times we take sigma s prime p s prime given s comma a times vn of s prime. Okay, so this is basically the simple Bellman update that we have been looking at. Now, if you think of it intuitively, what does this equation, what does this particular equation, let's name it equation 1. Maybe I highlight it. Yeah, yeah, let's do this. Let's highlight this with something like orange. Okay. So what this particular equation tells me here? Okay, so what it is telling me is that for any update of the value function that I need to undertake, okay, any sort of update for vn plus to in order to update vn plus 1, I need to have an idea of complete v of n. Only then I can update v of n plus 1. Correct? The reason being because there is a max term in this equation. Okay. So in order to do a max, I can only do a max if I have access to all the VNs. So think of it like this. So if I have a bunch of different states, so let's say I have my state space. Let's say my state space. Let's say I have some 4 states. Okay. So let's say I have states S1, S2, S3, S4. Just for an example. Okay. So my V of n can be thought of as an array, as a vector or as an array. Okay, let's think of it as an array for now. You can think of it as an array, which is vn of s1, comma vn of s2, comma vn s3, comma vn s4. Okay, if you think of it like this, so in order to change it to vn plus 1, what I'll do is I'll simply take some max of some quantity plus some gamma times some other quantity, which is the p of s comma a times vn. Okay, something like this. So basically what I'm trying to do is take a max over all the actions in a particular state. So uh, so each state would also have some action, right? So let's say state s1 has actions a1, a2, a3. Okay, so all I'm trying to do is trying to take that particular value function which maximizes, which gives me the max of a, right? So that's the whole idea when I do this update. Okay. So that means in order to make any such update to the value function, if I go back to this update figure, so any sort of update that I need to make to the value function. So in order to update s, I need to have a complete information of this quantity. Okay, I need to have a complete breadth-wise information of s plus 1 of all the corresponding next states in order to update the previous state. Okay, so you see that you can quickly see that as the MDP, as the size of the MDP increases, the solution becomes intractable and very easily computationally expensive, right? Again, so look at this equation. So let's say you have, okay, got hanged again. Okay, sorry. So yeah, so imagine you have some state S1. Imagine you have some state S1, after which the first uh, action that you take, first deterministic action that you take leads me to a terminal state. Okay, so any deterministic action that I take, so because I'm looking at a deterministic action, there's only one particular action that I can take. So let's say it gives me a reward of +1, and I end up at the terminal state. Okay, so what this equation tells me is that since the value function for a terminal state is inherently zero. Okay, so what it tells me is that in order to update S+1, I need to make one update. Okay, similarly, if I have some other state S2, which also takes one particular action and goes to the terminal state, there also I need to make one update of the value function. Okay, now let's say I'm two-step away from the goal, two-step away from the terminal state. Let's say I am in state S3. Okay, and then S3 goes to S1. Okay, so now in order to compute the value for S3, I need to make two updates. First, I need to make an iteration to compute the value of S1, and then after that, I need to update to compute the value of S3. Okay, so this is basically the comes under the dynamic programming method, right? Because I am using the value of state at step n to update the value of state at step n+1, which is the basic idea behind the dynamic programming method. Okay, so we saw two different types of value computation method. One was the value iteration method. Okay, this converges to V star and pi star. Okay, and similarly, we had the policy iteration method. And again, this also converges to my V star and pi star. So both these methods fall under the DP method, DP approach methodology. Okay. Similarly, similar to dynamic programming, there is something known as asynchronous DP. Okay. Okay. So what asynchronous DP does is it's basically dynamic programming only. Simply put, it's dynamic programming, but the array updates are in place. Okay. What do you mean by, or what do I mean when I say that the array updates are in place? Okay. So if you look at this equation, look at equation one. So you see, in order to compute the new value, which is v of n plus 1 for given state s, I need to factor in all the different vn of s and some, like, consider all the state vn at different states, and then take a max over that element. Okay. Now, what asynchronous DP tells me is that I need not necessarily be sequential in my approach when I'm trying to update the value function. So you think of it like this. So you have an array of v of n. You, when you are at time t plus 1, you basically copy that array, you copy it into a new array, and then you make changes accordingly, and then you use that new array. Okay. So you are creating copies of array and then updating it. But what asynchronous DP does is, we are saying that any update to the value function that I make, this will be in place. So if I am trying to update only for state S1, okay, so I have seen state S1 till now and I want to make an update for it. So I need not necessarily wait for an entire sweep of the state space in order to make a single update to the value function. If I have an update for state S1, I simply update for state S1 and I replace it in that array itself. Okay, so let's say I have seen state S1. Okay, so I update it with uh, Vn plus 1 S1. So I replace Vn of S1 by Vn plus 1 S1, so which is the updated value of S1. Now, later on, if I want to update state S2, state S3, and S4, so I'll continue to use the older values of S2, S3, S4, my Vn values, but for state S1, because it has been updated, I'll try using Vn n plus 1 of S1. Okay. And similarly, if I update S2, all the previous states before that will use the new value update. All the states that come after use the old update. Okay. So this is kind of an in-place operation if you look at it closely. I am not using any different sort of a uh, memory to memory to create an extra array and to make a sequential sweep over the entire state space. So this method kind of offers me flexibility in the sense that I need not necessarily have to wait for all state updation. I can do individual state updation that also in place in the asynchronous DP method. So here there is one simple assumption. The assumption is that in asynchronous DP, the assumption is that to ensure convergence. So turns out this method also converges. Okay. This method also converges, and to ensure convergence. So the thing is that sample all states infinitely often. Okay. This is an assumption that you make over here. The reason is that in DP, the convergence always occurs in the n tends to infinite limit. Okay, so the convergence is asymptotic in nature. So you need to sample all states infinitely often in order to converge to the optimal solution for a DP, right? So this is what asynchronous DP was about. Similar concept to that, and something which is very useful whenever we look at the control aspect for Monte Carlo or TD, an approach which is known as generalized policy iteration. Okay. What it simply does is you have a policy pi. Okay. You use that policy pi to basically evaluate your Q function. Okay. You use your policy pi to evaluate your Q function or your V function, any value function for that matter. So let's say I go with Q for now. I'll tell you the reason why I'm using Q. But let's say what I do is I given a policy pi, I solve for the value function, here the q, and solve for it using the Bellman equation, get the new q, which corresponds to my q pi, which is the updated q pi, and then simply I am, instead of following that particular policy pi again in order to update it further, I simply I simply become greedy with respect to that, with respect to the q function. Okay. So initially what happens is whenever I want to make a q function update, I usually fix a policy pi. Then I solve the Bellman equation iteratively until and unless I converge to a fixed point, which we have seen in the previous lectures. And after that, whatever q value we have, we see that if the change between the two subsequent steps is very minimal, then we return that to be the q pi, or we return it to be the fixed point for that particular contraction operator, right? Now, instead of that, what I'm doing is, for one step, I'm iteratively updating the q value. And second step, I no longer follow that policy pi. Next is, I become greedy with respect to the updated q. Okay. So this happens iteratively. So eventually, what you end up with is that you, so if you do it a lot of times, eventually you will converge to the optimal pi and the optimal value function. Okay. So this is given. Now, this is the idea behind policy iteration. So when we say generalized policy iteration, I'm using similar idea as that of the asynchronous DB. It's basically in place policy iteration. Okay, I need not necessarily create another array or create any separate memory in order to make the updation. So this is a generalized policy updation, and this is an in place operation that we are making over here. Okay, fine. So now let's take a very simple example. Okay. So we take a look at a grid world kind of an example. So let's say I have a 4x4 grid. Okay. I have a 4x4 grid, and these two corner boxes correspond to my terminal state. If I reach the corner box, then the episode ends. I consider the episode to be a success. Okay. And let's say I number this here. I'll number it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. So this is a grid world kind of an example. So there is an agent in the environment, and the agent can take 4 different actions. The action being, it can go up, down, right, or left. Okay. So these are the 4 actions that the agent can take. And the reward is as follows. So the reward for not reaching the goal is -1. So every step that you take where you don't reach the reward, you get you get reward of -1. And if you reach the terminal state, you get a reward of 0. And here, uh, think of it like this: if I am at the boundary, okay, so if I am at, let's say, state 3, and I want to move right, I know that it's not possible because the grid ends there. So if I try to move right, I won't move right, but I'll perform one step. So it's like I won't move right, but I'll still get a reward of -1 because that is one particular action that I have taken. So here it's like this. My probability of going from the probability of me going to state 6, given I was at state 5 and I took action R, is 1. Okay, this is clear from the diagram. Similarly, the probability of me going to state 5, given that I am in state 10 and I take action up, is 0 because I can't directly reach from 10 to 5 by taking the up action. Okay, and similarly, the probability of me going to state three, if I start at state three and I go to towards the right, okay. So it turns out if I'm at state three and I move towards the right, I won't be able to go because there is nothing over there. I'll stay in the same state, but I'll get a reward of -1. Okay. So this is a very simple example. Now let's see how dynamic programming approach can help us solve for this particular problem. Okay. So there is a particular code snippet that I have. So I'll just share the screen. Let me know if you can see it. Okay. So I've opened a Jupyter notebook. Please let me know if you can see my screen. Okay. So I will share this code with you on the chat. You can open it simultaneously. I'll also share it where I have shared all the resources. So, okay. So I am taking that same problem and have formulated into a code wherein we'll solve it using a dynamic programming method. Okay. So first I'll import all the necessary Python functions. And here we are looking at policy iteration. I don't want to deal with value iteration right now because we know both are two different types of dynamic programming methods. So I'll stick with one dynamic programming method, which is the policy iteration. So I have my gamma to be 1, which is my discount factor. My reward size is -1, which is the immediate reward. Okay, for any other state. My grid size is 4. My termination states are 0, 0 and grid size -1, -1. So it's like the top left corner and the bottom right corner. Those are my termination states. And the actions are to go up, down, left, right. So this is basically the coordinate which I can move to. So if I say action is -1, 0, that means I move to the left. If it's 1, 0, I move to the right. Similarly, so this is basically one step I'm taking in the positive x-axis, y-axis, or the negative x axis, y-axis. Okay, and I do it is showing access denied. Okay, now I think it should work. Okay, so this only has a viewing access. So if you want to make any edits, you should go to the file. You make you make your own copy of this code, and then you can make changes. Okay, so you can save and make a copy of this code. So right, so this is the parameters. Similarly, this is a function wherein I compute the action reward function. Okay, so given any initial position and the action, I compute basically whatever final position I'll go to and the reward I get. So this is a function to compute that particular value. Then I initialize my value map and the states. Okay, so for a grid size 4 cross 4, initializing all values to be 0 initially. Okay, and here I am performing the policy evaluation step. Okay. So what I'm keeping a track of is basically the deltas. So the deltas here basically is basically if you have seen the lectures. So when we talk about TD error, okay. So it's basically when we talk about stochastic averaging, because when we are doing it iteratively, so you have new estimate is equal to old estimate plus alpha times the target minus the current estimate, right? So this target minus the current estimate is termed as delta over here. So basically, I'm keeping a track of the delta here. So what basically I'm trying to do is what is the original target and how far off I am from the target. I'm keeping a track of that. So if my delta becomes 0, that means my DP code has converged. Okay, so this is for checking the convergence. Okay, so I just run this code, but okay. Okay. So if I run this code, so I have run it for 1000 iterations. So in the first iteration, this is how the value function looks. Okay. So initially you start off with a very random policy. You can at any given state S, you can move in either of the directions and all of them has equal probability. So that's why when you're closer to the goal, so that value function gets updated because it's any random action, you have a higher chance of reaching the goal if you are one step away from the terminal state. Okay. And similarly, you have iteration 2, iteration 3, iteration 10, and so on. So after 100 iterations, this is how the plot of deltas versus the iteration looks like. Okay. So as we increase the number of iterations, the delta values basically become zero. Okay. So this is the strength of a dynamic programming method. Okay. So just keep that example in mind. So now we'll go to the Monte Carlo methods. I will uh, come to that once we finish that. So we'll just keep that example in mind. Okay. So I'll just share my iPad screen again. Okay. So now we have looked at what we mean by dynamic programming. Okay. The second class of or a second type of method to solve a reinforcement learning problem or to solve an MDP is something known as a Monte Carlo method. So any idea what we mean by the term Monte Carlo? Just a second. I think screen got stuck again. Are you able to see my screen or is it stuck? Can you hear me? Uh, I'm not able to make any changes. Okay, fine. I think we are back. I don't know. Strange. I'm using the same Wi-Fi connection, but one place it shows no internet, but my audio is clear. So surprising. Okay, so far what we have seen with a dynamic programming method is that we are basically trying to use the value of we are using try to use the value estimate at step n to update for the value at step n plus 1. Okay, so this method is something known as bootstrapping. So when I say bootstrapping, I am using the word called bootstrapping. Okay, so bootstrapping means use previous estimate to update current estimate. Okay, so this method is known as bootstrapping. So this is what dynamic programming has been doing, right? So I am trying to take a backup of all the states, and especially for dynamic programming case, I am dealing with the full backup, right? Because I need to do a complete sweep of the state space in order to take a backup, and this is known as a full backup. So in Monte Carlo, instead of taking having the full backup, okay. So if I want to do a full backup, I need to know the model of the uh, MDP. I need to know the policy. I need to know the reward distribution. Okay. Now, turns out that usually people don't have access, or in many MDPs, in real life situations, you don't have the uh, policies defined a priori. Okay. So what you work with is known as a sample model. So here, instead of a full backup, you're doing a sample backup. So what you're trying to do here is, let's say you have your value function. Okay, the basic definition of a value function, if you go back to its crude definition, it's nothing but the expectation of the return GT given I start at state S and I follow policy pi thereafter. Okay, this is a simple pure definition of my V pi. Okay, now think of it like this. Let's say I start with some state S and then I basically follow policy pi. I have a policy pi. I follow policy pi, and then I take action A. Then I take next state S, then state S2, action A2, state S3, action A, and so on. And I keep doing that until I reach some terminal state. Okay. So this trajectory consists of a sequence of state action reward, and so on. Okay. And once I have that, once I reach the end of the episode, or once I reach the terminal state, then I get the full return, and I use that to update the value of state S. Okay, so this is one such trajectory. Okay, this is one such trajectory. I can take another trajectory. Okay, following policy pi, I draw another trajectory till I reach a terminal state, and once I reach the terminal state, I have another GT estimate. So I'll call it GT of 2 because the superscript corresponds to the different trajectories that I'm taking. Okay. And similarly, I can take capital N such trajectories by following policy pi, and I can get N such returns. Okay. Now, once I have N different returns, I can simply compute the expectation with respect to policy pi. And once I have computed with respect to policy pi, I end up with a value function. Okay. So this is a simple method wherein instead of having the full state space knowledge, I'm trying to do a sample of a trajectory. Basically fixing a policy pi, I am sampling the actions according to policy pi, get the next state and so on. And I draw multiple such samples and I take that. Because I reach the end of the episode, I can compute my GT because GT is only computed once I reach the end of the episode. And once I have a bunch of different GTs, I just collect it and average it over. So this is the basic idea in which V pi of x is calculated. Now, if you look at this approach carefully, you will see that what you will see is that you don't need any knowledge of my P S prime comma S comma 1. Sorry, you don't need to have any knowledge of the probabilities, okay, which is P of S prime given S comma A. You don't need explicitly that particular probability. You are simply filling a policy pi, drawing samples, and making updates over that. So this is kind of a simulation model that you are doing. Okay. But turns out based on different simulations that you do, based on different simulations that you are able to make some crude approximation of the probabilities that is inherent in the MDP. Okay. You don't explicitly have access to it, but based on multiple simulations, you are making some estimation. Okay, this is the general idea. So yeah, idea is you fix policy pi, then generate okay, I think recording stopped again. Let me see if I can connect with my mobile hotspot. I hope this is smoother now and there are no further disconnections. So the idea behind Monte Carlo is that you fix a policy pi and then you generate many trajectories. Okay, so this is like the approach for Monte Carlo methods. Cool. So here turns out that trajectories in this case gives me the states as well as the reward. Okay, because eventually what I'm getting is my reward GT. In case of dynamic programming, I only get a new state, a value function for new state, but I don't get necessarily a reward. Okay, so this is another advantage here. And what happens here is, so for a particular state S, okay, I fix policy, I generate multiple trajectories, and whatever update I make, that update is only for state S. Okay, so if I consider any other uh, state here in between, okay, so let's say this, if I consider some state that falls in on the trajectory, so I'll call it state S1. Okay, so any state that falls within the trajectory according to policy pi. Okay, if I start from state S. So can I use the information of S1 to compute the values for uh, the value function for S1? If I'm following the same policy pi, then yes. If I I fix policy pi, then I can use that same S1 to I can use the same trajectory updates to update for S1. But there is a small catch in this method. So it turns out that only if I am following policy pi, so if I follow policy pi from state S, there will be multiple times that I'll encounter state S1. In comparison, if I start from state S1, then I might follow some different policy pi. Okay. So it need not be that the policy pi that I'm following from state S be same as the policy pi that I'm following from state S1. Okay. So you see, if I try to update all the in-between states, like state S1, S2, that falls under the trajectory when I start from state S. So the number of trajectories that I generate from policy pi will be disproportionately larger than any other policy that will be generated from state S1. Okay. So turns out that any such kind of a method, this don't get guarantee convergence. Okay. Such kind of methods don't guarantee convergence. Although in real life scenarios, it is possible to, solve for it, but mathematically they don't guarantee convergence. Okay. So what you're trying to do is I'm only trying to update for the initial state S, and I don't try updating any state that falls in between the trajectory. Okay. So now turns out all this update I'm doing is for one state S. Okay. Once the episode ends, I again go back to my starting state S. I again draw out a trajectory, make an update, and come back. Okay. So in order to make a complete exploration of an environment, what we need to do is we can't always come back to the same starting point because there might be certain states that may not be visited based on policy pi. Okay. So in order to make like update sufficiently large number of states in the entire state space, there is a method people use which is known as exploring starts. Exploring starts. So what happens in exploring starts is that after you reach the terminal state T, you don't reinitialize your state back to status. You reinitialize some random state in the environment, and then you draw trajectory from that. And after the episode end, you again initialize some new state S, and then draw trajectories from that, and so on. So this somehow allows exploration of the state space in the environment. So this is what we mean by exploration starts in Monte Carlo. And in Monte Carlo, the update that you're doing, it can be done in two ways. So one method is known as first visit Monte Carlo, and the other method is known as every visit Monte Carlo. So what happens in first visit is, so you only take into account the first occurrence of the state, and any subsequent occurrence of the state, you do not care about that. And all the updates that you're making is only based on the first visit that you have made to that particular state. And similarly, in every visit, you take into account all different occurrence of state. Okay. Now, turns out in most of the cases, or for the purpose of this course here, we will typically be dealing with first visit MC only. So there are certain advantages that every visit MC has over first visit MC, but eventually, eventually both of them converges to the same policy and the same value function. Okay. So for this purpose, we'll stick with the first visit MC. Now, this was Monte Carlo approach. Okay. So far we have seen how we can evaluate a particular policy. So we have an evaluation metric, which is my VPI. What my VPI tells me, how good a particular policy is starting from state S. Okay. So all I'm doing is predicting how good a state is. Now I want to look at Monte Carlo controls. Okay. So when I say control, what I mean is, given an updated value function, how do I extract policy pi from that particular value function? Okay. So turns out we have already seen actually in 2, 3 slides back how we do that. We do that using GPI. GPI stands for generalized policy iteration. How it works is, you basically update the value function and then you behave greedy with respect to that value function. Okay. So now if I want to get policy pi at time t plus 1, I want to get policy pi at time t plus 1. So I can do it like this. I can do argmax of no. So I can do argmax of q given s comma a, right? So here I'll not use a value function, but rather I'll use a q function. The reason why I'm trying to be greedy with respect to q function is that if I instead choose to be greedy with respect to the v function. Okay, so being greedy with respect to the v function would require me to have knowledge of my okay, so I need to have knowledge of the policy and I need to have a knowledge of the model. Okay, but because I'm doing Monte Carlo, the purpose why we have shifted towards Monte Carlo or why Monte Carlo over dynamic programming is that we don't want to deal with the model as such. Okay, so that's why it turns out if we have the Q value update, I can directly be greedy with respect to that Q function, and that will recover me the optimal policy. Okay, so that's why whenever we are dealing with control meaning whenever we want to recover a policy from a value function, we always start with the Q function. Okay, what happens in Q function is instead of state S, you start from a state action pair. You fix a policy pi, you draw some trajectories until you reach a terminal state. You get some returns and so on. Okay, similar to what you have been doing in in V in V of S. Here instead of behave behaving according to policy pi from state S, you start from state S, you take action A, and after that you follow policy pi. This is the only condition here. The first action that you take is fixed, and after that you follow policy pi. Okay, so you always start with a state action pair. Now, again, similar to that, if I take any random state S1, A1, something like that in between, okay, which falls under trajectory, which falls in the trajectory if I am following policy pi. So if I try to update my in between points that fall under the trajectory, turns out that the number of samples that are generated according to policy pi will be much, much larger than any other policy that will be followed if I start from S1, A1. Okay, so that's why there are issues with convergence. So all the update that we are doing is only on the initial state action pair. Any intermediate state action pair that comes in the trajectory when I'm following policy pi will not be touched or will not be updated. Okay, and hence because I'm only updating the initial state action pair, right? So I need to have different state action pair combinations. Okay, only then I can draw sample trajectories from a state action pair and update on that. So hence we have to use exploring start methods, right? So that after the end of the episode, I reinitialize with some new state action pair, and then I again sample trajectories and make an update. Okay, so this is necessary. Nothing else. Uh, what if I don't want to use exploring starts? Okay, what if I don't want to use exploring start? So let's say I want to work with a non-exploring start Monte Carlo, a non-exploring starts Monte Carlo. So the MDP that we have had so far was a deterministic policy, right? The pi that we had so far was a deterministic policy. That's why here my A1 was nothing but state of pi S1 according to policy pi. Okay. So this was a deterministic policy. So if I want to remove the exploring starts part from the MC, if I want to go for a non-exploring start, I have to relax the assumption that my policy is deterministic. Okay, you relax the deterministic policy constraint. Okay, so when I say relax deterministic policy constraint, what I'm trying to say is instead of having a deterministic policy, I'll have an epsilon soft policy. meaning the best action, instead of having the best action having the probability of 1, it will have a probability of 1 minus epsilon, and all other non-optimal actions, okay, will have a small epsilon probability. So we are keeping some sort of exploration. Okay, so this, if you look here, would be similar to what uh, epsilon greedy does in the multi-arm bandit problem, right? So all I'm doing is, instead of a deterministic policy wherein each state will have only one action, I'm relaxing that assumption. I'm saying there are multiple actions that are possible from state S. The best action will have the bulk of the probability. All other actions will have a small epsilon probability. Okay. Now turns out if I make this particular relaxation, if I deal with an epsilon soft policy, then this converges to an epsilon optimal policy. Okay. So this actually guarantees an epsilon optimal policy. And based on the control over epsilon that I have, I can control the uh, optimal solution that I want to achieve. Okay. So this is something known as a Monte Carlo method. More specifically, this non-exploring, this epsilon soft policy Monte Carlo is known as on policy Monte Carlo. Okay, this is known as on policy Monte Carlo. The reason we call it on policy is that any sort of trajectory sampling that I'm doing, I am behaving epsilon greedily when I'm doing a trajectory sampling. And the updates I'm doing are basically the the updates that I'm doing is also on the same particular trajectory. Okay, so I'm behaving on that same particular trajectory and I'm updating that same particular trajectory. But since for an on policy Monte Carlo, I have relaxed the deterministic policy constraint, the solution that I want, typically, it doesn't give me the kind of solution that I want for solving an MDP, right? It still works, okay. In practice, if you solve for an on policy Monte Carlo method, you will still converge to the optimal policy. But even for an MDP, we so far have been looking at a deterministic policy, right? So turns out, if I want to still remain the deterministic policy zone, as in I don't want to have a stochastic policy, I still want to keep a deterministic policy. So what I need to do is I need to uh, behave according to some different policy and evaluate some different policy. If I can somehow decouple the behavioral part and the prediction or the estimation part, that makes my life good. And that decoupling is basically known as off policy Monte Carlo. Off policy Monte Carlo. Okay, you have a different policy for evaluating and behaving. Okay, so the trajectory that you have updated, you need not necessarily follow that particular trajectory. It turns out that you can follow some other trajectory and use it to evaluate some other trajectory. Okay, so the way it works is, okay, let's get away from MDP formulation. Let's deal with simple expectation. Okay, let's say I want to compute the expectation of some function f, wherein the random variable is sampled from a probability distribution p. Okay, so the way it works is, you do sigma x px of x, right? This is how I compute an expectation. And if I want to uh, like do it in a sample based manner, I can write it as approximately 1 by n PXI, FXI. Okay, this is how can I can approximate this particular expectation. Okay, so now turns out that in some cases it might be very difficult to sample trajectories. So here, let's say xi is the trajectory. Sometimes it might become very difficult to sample random variables from a probability distribution P. It turns out you have some other simpler kind of a probability distribution, and you would like to sample for that. Using that, you would like to update f of x. Okay, where my f of x is falling starting from some different probability distribution, but the update that I want to make is on basis of another probability distribution. Okay, so I'm trying to basically get to the idea of off policy MC. So what happens is, what I can do is, in this case, I simply add an extra term. I multiply and divide by that. Okay, and then I write it like this. So this particular expectation has been converted to an expectation of some other quantity, wherein the x's are sampled from a new probability distribution Q. But these two expectations, my expectation EF of x is equal to EFX PX by QX. Both are equivalent, right? Which we have shown. And if I were to write the approximation part here, it will be FXI, PXI, QXI. Okay. And turns out you need not always have to approximate it by 1 by n. Okay. The reason being, so the reason being that turns out if the ratio of PXI QXI is more or less comparable throughout for all i's, if my ratio of PXI QXI is comparable throughout, then taking a sample, a simple average, a 1 by n average gives me an approximate solution. Okay. So this is based on the assumption that my policies, my uh, new distribution Q is somewhat, you know, closer as my new distribution Q is somehow related, closely related to my old distribution P. Okay. If they are somehow closely related, then you can simply do 1 by n sigma fxi pxi qi, and averaging over that will give me a rough estimate of this particular quantity. If that is not the case, if the ratio of pxi and qxi is very, very large, okay, so this 1 by n method fails. So what you do is something known as normalize, you normalize it. Okay, so instead of 1 by n, what you're doing is you keep everything as it is. Okay, so this is the numerator, and instead of 1 by n, you divide it by sigma I to n pxi qxi. Okay, so this is known as normalized importance sampling. The earlier method here was known as importance sampling, by the way. This method is known as importance sampling. Okay, so this is just telling about important sampling. Now, if we come back to the MDP problem again, so we were looking at off policy MC. Okay, so we'll be using ideas from important sampling to define off policy MC here. So here my xi, which was a random variable in the above equation, here would correspond to trajectories. So trajectories like I have some initial state as 0, action A0, reward R1, S1, A1, R2, and so on. So xi is basically a trajectory that I have. So here Pxi is basically the probability of me actually following that trajectory. So that is given as like a chain rule that you do. So you take probability of S0, pi of A0 given as 0, then P S1 given as 0 A0, pi A1 given S1, and so on. Okay. And similarly, my QXI would be P S0, mu A0 S0. I'll just define mu in a moment. Okay. So my pi is the policy which I'll be estimating on. Okay. So the estimation that I'll be doing will be on policy pi, and mu would be the policy which I'll be behaving on. So my mu is basically the behavior policy. So think of it like this. If my mu, so come back to the important sampling. So this only works under the condition that my q of xi is always non-zero, right? If q is 0, then importance sampling is undefined in this case. So that means I have replaced my p by the estimation policy and q by the behavioral policy. So my qxi can never be 0. That means my behavioral policy can never be 0. So when I say that my qxi is non-zero, this in a way means that the policy I'll be having is an epsilon soft policy. I no longer will be following a deterministic policy. The behavior policy that I have, I'll deal with an epsilon soft policy. Estimation policy need not be epsilon soft. It could be a deterministic policy. That doesn't matter in this case. Okay. So now, if I just take the ratio of Pxi, Qxi, you get pi of A0 S0, pi A1 S1, so on, and mu A0 S0, mu A1 S1, and so on. So if you look at Pxi, Qxi, you will see that computing Pxi is a difficult task. Why? Because I need to have my probability, the transition probabilities, which is P of S1 given S0 A0, P of S2 given S1 A1, and so on. And the reason we are doing Monte Carlo is we want to avoid doing that. Okay. So computing Pxi, Qxi is difficult. But turns out if I take the ratio Pxi, Qxi, and that's what we want to do in importance sampling, then all the PIs get cancelled, right? So all I'm left with is basically a bunch of policies that is mapping me from state S0 to A0, S1 to A1, and so on. Okay, according to the policy that we have. Cool. And can write it as some for some time horizon t. Can define it as AJ given as J mu given this. Okay. Now, if we look at the original equation that we had, I'll write it here. If you look here, so my expectation of E f of x, so my f of x in this case, if my xi are the trajectories, so this uh, f of x that I'm evaluating would be the reward, correct? So the if xi is the trajectory, if I have defined my xi's to be trajectories, so my f of xi would be the corresponding reward. And if I want to take the expectation of a reward or the expectation of a return, that is nothing but my value function, right? So my LHS is simply the value function, and RHS is, I'll just substitute for fxi, which is gt of I capital pi j0 to t pi ajsj mu ajsj, okay, divided by sum over the products of pi ajsj and mu ajsj. Okay, so this is how one can typically work with an off policy Monte Carlo setup. So turns out on solving this, the policy that you will get will be deterministic in nature. You won't necessarily have an exploratory policy. The policy you will get for an off policy method will still be deterministic. Okay. But the behavior policy that you are dealing with should be epsilon soft. Okay. So this is the basic idea behind Monte Carlo that we have looked at so far. So again, we'll go back to the grid word problem. If you remember the problem, so 4x4 grid, top left, bottom right corner are the terminating states. Rest all. Any random step that you take will give you a reward of -1. Just let me share it again. Let me know if my screen is visible. Okay. So we'll start with the Monte Carlo methods now. Okay. Similarly, same problem. I have my parameters defined same. So here I've kept gamma to be 1. My discount factor is 1. Reward is -1 and so on. And then initialization is I initialize the grid size. I define the returns, deltas, and the states. And here this is a function to generate episode. Okay. And based on that, what I do is for number of iterations, here the number of iteration is 10,000. I generate an episode, and based on that, I compute the return and do the update over here. Okay. And the episode generation is random in this case. Okay. According to some policy, some heuristic policy pi, but in this case, let's say the policy is a uniformly random policy in this case. If I run this, okay. So I'm running this for 10,000 iterations. This exploration, uh, ex exploratory start sampling. So this is for a first visit MC case. Okay. So this is how the value function looks like. And for gamma equal to 1, if I plot the delta plot, okay, the error plot. So this is how it looks. So this different lines correspond to the different states. Okay. So since I have 16 different states, right? So each state will have its own corresponding target and its own corresponding estimate, which is V pi of S, and the target, which is expected of RT given state S. Okay. So there are 16 different lines, and this is how the trajectory looks like. Okay, turns out in comparison to the dynamic programming method, which converged only in 1000 time step, but it also had a complete information of the state, right? Here, I don't have a complete state information. Rather, I only have samples that I'm generating through experience. And based on that, I'm learning. Okay. So the convergence here is still happening, but it's not as smooth as compared to the DP part. Okay. Now, if I go back and I change gamma, okay, let's say I decrease the gamma, make it zero point 0.6, the discount factor. Okay. And I run everything again. Okay. This is how it looks. And this is, I'll plot for gamma zero point 0.6. Okay. Turns out with gamma zero point 0.6, if I'm reducing gamma, it's a smoother convergence, right? As compared to gamma 1. So based on the different tunings of the hyperparameters that you have, which is the gamma in this case, you can actually show convergence in this case. Okay. So this was about Monte Carlo. The last thing to cover that I want to cover today is temporal difference methods, right? So we'll quickly go back to that and come back to this example again. Okay, now if you look at the two approaches that we have seen today, one is the dynamic programming approach and one is the Monte Carlo approach. Okay, so I'll again draw this diagram. So this corresponds to action A and the reward R. And this happens till I reach some terminal state, right? So this is the dynamic programming part. And for Monte Carlo, it's like for a policy pi, I'll simply generate a trajectory till I reach some terminal state T. And based on that, here the update will be towards the upper part of the tree. And here, once I reach the terminal state, I'll get the complete return GT, okay, and use it to make an update, okay. So the idea is this is dynamic programming, okay. This is dynamic programming. This is Monte Carlo. So in dynamic programming, there is full backup, which is happening, okay. So the backup that I'm doing is over the entire state space. I have a complete access to the transition probability and all the states are available, like the full information is available to me. And based on that, I'm just making a full backup, okay. And the backup is done by a method known as bootstrapping, okay. In comparison, in Monte Carlo, there is only sample backup and no bootstrapping. What is bootstrapping again? I had mentioned this Do you want me to repeat it? Or okay, I'll only repeat if you want me to. Otherwise, I'll assume you are aware. Bootstrapping, okay, means that you are using a previous estimate to make a current estimate. Okay. So typically what happens in Monte Carlo is you relax the Markovian assumption. Okay. When I'm dealing with Monte Carlo method, I no longer deal with the Markovian assumption or the Markov property. That means if I am at state S, I don't care how I reach state S. Okay. State S is from where I start. How I got there, I don't care. And based on that, I'll just keep moving forward. So any state in between, if I want to make an update for that, I don't care how I got to state S plus like S prime or S double prime or any other new state. I just take it as my starting point, draw samples, and make update. Okay. So that's why there is no inherent bootstrapping which is happening. So the Markovian property doesn't hold true for a Monte Carlo method. For our dynamic programming, yes, Markov property holds, but the backup is an issue. Okay. So it turns out there are two good things. Okay, in Monte Carlo, sample backup is a good thing. In dynamic programming, bootstrapping is a good thing. So temporal difference basically combines the best of both. Okay, so you can think of it like my temporal difference is basically sample backups plus bootstrap. Okay, both these combined. Now this method of temporal difference is somehow like the crux of what the reinforcement learning course is about. Okay, it's like the heart of RL in this case. Like, so what happens here is you have an initial state. Okay, maybe I should draw it first. Let's say okay. So temporal difference is basically prediction at time t plus 1 is used to update prediction at time t. Okay, so I go one step ahead in time, take all the information, new information that I get, use that to update the prediction that I had in time t. Okay, so this is a general idea behind temporal difference method. Again, if we start with what I want to do with Monte Carlo, I want to estimate this quantity, which is expectation of GT given ST is equal to S, which is the value function that I want to estimate, right? But I don't have expectation of GT in Monte Carlo. All I have is some GT, which is a sample that I draw from the expectation value. So I have a bunch of different GTs, and based on that, I take an average over that and I update my value function. Correct. Now turns out there is an incremental way in which Monte Carlo can be done, right? So my incremental Monte Carlo can be done by my incremental Monte Carlo can be done by a method called stochastic averaging. Okay, now we are again going back to what we did in the beginning of the course when we started at week 2, when we started with multi-arm bandit. Okay, so we discussed, at least I discussed in great depth what we mean by stochastic averaging. Okay, so it's a very simple formula. I'll again write it down. So my new estimate is basically old estimate plus step size target minus old estimate. Okay, this we again came back to this definition. So when I want to like update this value function, okay, so this is v of s, right? When I want to update v of s based on the samples that I'm getting, the sample returns that I'm getting from a trajectory. So this is how it looks. So my v new of s is basically v old of s plus step size, which is alpha here. The target here is GT. Okay. So I'm trying to be closer and closer to GT. But because, uh, okay, let me just write it now. So first, okay. So the target ideally should be expectation of GT. But here I'm taking an estimate of GT, an estimate of the expectation in the above line. Okay. So this method is known as stochastic averaging. Okay. This is stochastic averaging. And I'm simply using stochastic averaging for Monte Carlo. So it's an incremental way to update the value function in Monte Carlo methods. Right. Now we come back to the GT. What is GT in the beginning? If you start with the definition, my GT is nothing but RT plus 1 plus gamma RT plus 2 plus gamma square RT plus 3 and so on. Okay. I can write it as RT plus 1 plus gamma GT plus 1, right? Because it is going on for a long, long time. So I can write it as RT plus 1 plus gamma GT plus 1. So return at time t plus 1, discounted return after at time t plus 1. Okay. And turns out this can be approximated as RT plus 1 plus gamma times V of ST plus 1. So this is an approximation that I'm making. What is the approximation? The GT values that I get, I'll only get the GT value if I reach the end of the episode, right? But what if I'm taking only one step? Okay, I won't necessarily have the GT value. Like I'm taking one step and then I'm approximating the rest of the steps that I will take. That is estimated by V ST plus 1. Okay, so this is an approximation or that we have. So in a way, I'm truncating the length of the future rewards and replacing it by V pi of s, which gives me some approximate estimate of the future returns after time t plus 1. Okay, this is what I'm doing. So if I keep this equation in mind, I just replace this in the above equation, which is V hat of new s, V hat of new st is equal to V hat of old st plus alpha RT plus gamma V hat old st plus 1 minus V hat of old st. Okay, I have simply replaced GT by equation number 2. So this method or this technique is known as a TD0 method, or it's called temporal difference method. So we'll call it as TD0 for now. Okay. Now, intuitively, how it works is, let's say I start at state S. Okay. I take one action A. I move to some state. Let's say I'm at state ST. I take action AT. And then I move to state ST plus 1. So I'm trying to use, I take a one step sample. Okay. So in order to take action 80, I just took a sample action according to policy pi. I took one step and I made a backup. Okay. So I used the older estimate to update the newer estimate. So basically, the trajectory that I draw out is a sample trajectory. I'm not doing a full backup. I'm still doing a sample backup, but I'm again retaining the benefits of bootstrapping. So this is bootstrapping, right? I'm using V old to estimate V new, right? So this is bootstrapping in a way. So I'm still maintaining bootstrapping. I am still drawing a sample trajectory. So this method is combining both these approaches together. And what we end up getting is called TD0. Okay. Uh, Turns out that when we have TD0, this TD0 formalism, the Markovianness in TD0 is inherent in this case. Okay. So when we dealt with Monte Carlo, we say that this approach doesn't follow the Markov property. But when we introduce for the TD0, the Markov property is inherently built in this case. So this is another solid advantage that TD0 gives me. Okay. So turns out that both Monte Carlo and TD0 can give similar solutions, but depending on the application that you have, whether the problem that you're dealing with is Markovian in nature or non-Markovian, based on that, you can leverage both these approaches together. Okay. Typically, we deal with a Markov decision process. So that's why TD0 is generally beneficial in this case. Okay. So this was TD0. Now, after defining this, next step is definitely the control aspect of it. TD0, all we have been doing is dealing with the evaluation of a state. For control, again, we don't use the value function, we use the we don't use the V function, we use the Q function, right? So, similar update, all I'm doing is instead of V, I replace it by Q. So this is Q old STAT plus alpha times RT plus 1 plus gamma. Okay, gamma. Ideally, here I should put VST, right? Because that's what we approximated in this in equation 2, V of ST plus 1. But instead of that, I can say I'll put Q of ST plus 1, AT plus 1 minus Q. Okay, this is also Q old. This is Q old ST AT. Okay. So ideally, this should be V of ST plus 1. Okay. But again, I'm saying if I fix policy pi, okay, so I'm kind of generating a sample based on policy pi. So my BS of T plus 1 is an expectation of QST plus 1, AT plus 1. Okay. So instead of taking that that estimation, or sorry, the expectation, my bad. Instead of taking the expectation, I'm taking a sample from that expectation. Okay. So this is what I have replaced here for the control part. And turns out, once this is done, all you need to do is you learn the Q value function iteratively and then be greedy with respect to Q of SA. Okay. So this is the TD control approach for this kind of a problem. So instead of the V function, you make an update over the Q function. And once you have the Q function, you be greedy with respect to that. Greedy means pi is argmax of a Qs comma a. That's all you need to do. Okay. So turns out this is one naive method of getting the policy from the Q function. There are other ways in which there are two different ways. There are two popular algorithms known as Q learning and SARSA. Both of these methods are TD control methods, how you can recover the optimal policy from Q function. So we don't have much time left. Maybe we can uh, push it to the next class. We'll start from Q learning and SARSA. So I think this sort of conveys the agenda that I had in mind. So I wanted to basically showcase the difference between three approaches. One was the dynamic programming approach, one was Monte Carlo approach, and the last one was the uh, TD method approach. Okay, the temporal difference method, right? So there are certain advantages with each case. Okay, so finally we'll go back to the example that we had seen, the 4x4 grid world, and see how TD behaves. Okay, so let me share my screen again. Okay, let me know if it is visible. I think it is visible, right? Cool. So finally, we deal with temporal difference method. Again, I'll initialize all the necessary Python functions. For TD0, there are two factors, okay, that I'm considering. First is the gamma, which is the discounting rate. Second is alpha, which is the step size rate. Okay. For first case, I have kept gamma to be 0.1, alpha to be 0.1. Rest everything remains same. I do the number of iterations for 10,000 time steps. I initialize everything. All the utility function, which is generate initial state, next action, take action, all based on the policy of temporal difference. Okay. All of the functions have been defined over here, including the bootstrap part. Okay. And finally, for that many number of iterations, we just run it. I'm again storing deltas. Okay. Deltas is the TD error, the error term, which is inside the bracket. Okay. Which is target minus current estimate. So I'm storing this value. After 10,000 episodes, this is how the value function looks. And if I plot it, so you see this shows a very decent convergence in this case, right? So I have just plotted it for the first 50 iterations, but the delta values have, even though it's not smoother, but there are advantages, right? Because I am not dealing with the state transition probabilities. I only need to do a sampling along with bootstrapping, and this gives me a good convergence. So you say that this is a case of convergence. Okay. Now similarly, I'll try another case. I'll go here, maybe make gamma 0.9 and the step size also 0.9. Okay. And see how it reacts to this. So I'll run everything accordingly. Uh, okay, my bad. I'll go here, make 0.9, and this is 0.9. I run all functions, all the cells. Okay, so this was a plot for gamma 0.1 and alpha 0.1. Now, if I just for 0.5, right? Did I make it 0.5? Okay, I made it for 0.9. Okay, let's try for 0.9 how it looks. If both are 0.9, it's a very, very bad plot, right? So it's a case of no convergence. Fine. So turns out the tuning of the gamma and the alpha parameters play a significant role as far as convergence is concerned. So let's try finally with 0.5, 0.5. So this is for gamma zero point 0.5 and alpha zero point 0.5. Let's see. Again, this is somewhat better than the 0.9, 0.9 case, but somewhere midway, right? So again, this is a case of no convergence. Fine. Yeah. So I think this was all I had in mind. I have more content, but I think it's already 8 o'clock. If you have any questions, please feel free to ask. If you have any doubt with the implementation or any concepts that I discussed today, please feel free to ask. Otherwise, content wise, I have pretty much covered what I had intended to cover today. Maybe I'll wait till 8. If you have any questions, do shoot, or we can simply close the session. Okay, if there are no further questions, I think it's a good time to stop uh, today's class. Thank you for attending. We'll meet next week, same time, 6 to 8. Okay. Thanks a lot. Bye. I'll just stop the recording. Okay. Good night.